images. Let's look at the next question. It is about sequential data. Let's read the question. RNNs handle data with strong test dependency. The answer is sequential. Uh, RNNs, recurrent neural networks, are designed for sequential and time series data. What are temporal dependencies? Future values depend on past values. The order of data matters. So why standard networks are full fail for sequences? They ignore temporal relationships. They assume independence. They don't capture context. Let's see how NNS works. Rand state carries information from previous steps. Same weights used for each time step. Information flows through time. We also face some challenges in this, which are vanishing gradients, exploding gradients. Only remember short term dependencies. Let's see the next question then, which is about GANs, discriminators. Let's read it. In a GAN, the second model acts as a dash distinguishing real and fake data. The answer here is discriminator. GANs, generative adversarial networks, involve two networks competing against each other. Its structure consists of generator creates fake data and discriminator which distinguishes real from fake. Let's see how they work. Generator creates fake samples trying to fool discriminator. Discriminator tries to correctly classify real versus fake. Both improve through competition. Let's see the training dynamics. Generator loss increases when discriminator easily detects fakes. Discriminator loss increases when it misclassifies, ideally converges to equilibrium. Let's see the next question, which is about transfer learning. Let's read it. Reusing is a pre-trained model for a related task is called dash learning. The answer here is transfer. Transfer learning is one of the most powerful techniques in deep learning, especially when you have limited data. Here, the core idea is to use knowledge learned from one task to improve learning on a related task. Why it works? Each layers in deep networks learn general features like ages, shapes, colors, useful across many tasks. What are the advantages of transfer learning? Works with limited data. It works in faster training, better performance, lower computational cost. It does have some variations, which are feature extraction, fine tuning, domain adaptation. Let's look at the next question then, which is deep learning about wide and deep models. The question is the wide part of which is about wide and deep models. Let's look at the question. Yes. The answer here is memorize. Wide and deep learning combines two different network designs to leverage their strengths. Wide components are linear model, directly connects input to outputs, excellent at monitoring specialization patterns and rules, and it is fast and interpretable. Let's look at the deep components. Multiple hidden layers, learns complex interactions, generalizes patterns, slower but more powerful. By combine them, wide captures memorized patterns, deep generalizes learned patterns. Now look at the next questions. Uh, the next question is about deep features. Let's read the question. The deep part captures more dash features. The answer is here is abstract. Abstract means high level. Deep networks excel at learning hierarchical abstract representation of data. Why we use abstraction features? Because it generalizes across data, captures semantic meaning, enables transfer learning, aligns with human understanding. Let's look at the next question, which is about linear classifiers. Let's read the question. Linear classifiers combines inputs with dash to form predictions. The answer here is weights or biases. Linear classification classifiers form the foundation of all neural networks, even deep ones. Uh, let's look at the bias role here. Bias allows the decision boundary to a shift, not necessarily passing through origin. Uh, let's look at the next question. Activation. It is about activation functions. Let's read it. The activation function introduced dash into neural networks models. The answer here is non-linearity. Activation functions are actually crucial. Without them, neural networks would just be linear models. And let's see why non-linearity matters. Because it enables learning complex patterns, makes networks universal approximators, allows hierarchical future learning. Next question. It's about model complexity, and let's see the question. Adding neurons or hidden layers increases model dash. The answer here is complexity or capacity. Model capacity refers to the complexity of patterns a model can learn. Affecting capacity are number of layers, neurons per layer, and types of connections. Uh, the capacity implications are higher capacity uh, can learn more complex patterns, but risk of overfitting is there. Balance needed between capacity and data. Let's look at the next question, which is about transfer learning. Again, transfer learning leverages test features learned from prior tasks. The answer is representation, or the answer can also be here pre-learned or learned. We discussed the transfer learning before, but here it emphasizes feature reuse. So let's look at the next question, which is about. Uh, okay, we have finished our questions. This was the last question about transfer learning. Let's summarize this video by looking at the key concepts from this video. Uh, we covered deep learning as ML subset, specialized branch of neural networks, universal approximation, deep networks, layer connections, CNNs, RNNs, LSTMs, GANs, linear classifiers, activation functions, model capacity, and feature reuse. These 15 concepts represent the core of modern deep learning. And this brought us to the end of our video. Thank you for watching this comprehensive guide to section C. And in the next video, we'll discuss section D of my second internal. Thank you for watching the video.